So, recap our previous lesson. We went through properties of space-time, uh, went through general relativity, and showed how it predicts black holes, and introduced the beginning of time dilation and stuff. Um, I can give a more intense recap if you want, but I think that's fine. Um, so, I also wanted to. My original plan for this lecture was to continue and talk about coordinates and stuff, but I figured that it'd be better to honestly talk about action because I feel like it's an important principle and it's kind of the foundation of last week's thing, but I didn't really get to talk to it. I kind of dove right into black holes before I finished talking about action. So let's go over action. So action's mess looks like this. Probably seen it before. In SI units, which is like basically standard units, it is kilograms per, or kilogram meters per second, kilogram meters square per second, which is also, if you know like physics, it's joules per hertz or joule seconds, which is kind of a weird concept, but you can think of it kind of like that. That's a question.
What is hertz?
Hertz is the measurement of like a wave. It's like how large the waves are, if that makes sense.
Okay.
Yeah, vertical. And then the frequency is distance. So it's like frequency and hertz are opposite. Like, what do you call them?
For a sine graph, one would be the A value.
Yeah, one would be the amplitude.
The amplitude. And
Yeah.
the other would be P.
Yeah.
Okay.
Okay. So action is a complicated thing in physics. You basically see it everywhere. You see it in chemistry. You see it in quantum mechanics, which is also chemistry, I guess. But you see it in physics everywhere, literally everywhere. But it's not really like we don't talk about in high school physics for some reason. Maybe you do in physics 3, but we don't have that. So we might do it in college, but I'm not actually sure if, like, unless you have a specialized thing, we talk about it. So I said last week how space-time events are defined, or like the structure of space-time is determined by how, like, the path of least action for light, for how it can like go from one point to another, is like that tells you what the space-time is. But this is like a little inaccurate, as I'll get into later. But like Richard Feynman, who's like a famous science guy, I have a lecture if you want to look at him. He could kind of explain this in a different way, where it's not really least action, but it's more like if you have a curve of action. Well, I'll get to this, but if you have a curve of action, it would be like where the minimum is, because this is like a flat thing, and then up here it's like not a flat thing. So that's kind of, you probably can't understand what I'm talking about, but hopefully you will by the end of this.
Wasn't the higher flat thing up there?
What?
Why not the higher flat thing?
That's also a thing where it's a minimum versus a maximum. There's also something called, well, I'll just get into it. So, hi, fair. For a trajectory of a ball moving in the air on Earth, we can do an action thing. To give like an example of what an action, like how you would picture action, it would be defined between two terms in time, t1 and t2, because like one happens at one time, one happens the other time, and as kinetic energy, which is like energy that is, I would actually define kinetic energy as being non-potential energy, or energy that's like actualized. Like potential energy is energy that, like if I'm holding this pen, that's potential energy, because as soon as I drop it, well, that's probably not good for it. But sorry, Mr. Dare. But it drops because it has energy basically stored in it. So kinetic energy is energy like if I threw I'm not going to throw the pen, but if I threw well, actually, I guess if I threw the pen, it would, yeah. If I threw the pen, it releases kinetic energy. If I dropped it, then it also releases. Yes, question.
Are you putting force on it? Like, is that kinetic energy or is that something else?
Yes. Well, the kinetic energy is from the force, but yes,
Well, like when you throw it, what type of energy is that?
kinetic. But it's a ratio between kinetic and potential. I don't need to go into this, but it's
Oh,
because it's horizontal. Like as it goes down, the potential energy decreases and the kinetic energy increases. Yes, question.
How does this relate to interstellar and black holes?
If only I could continue talking about that. Thank you for the segue. Um, so we could represent the action as scary stuff. Whoa, whoa, calculus. Let's hold our horses for a sec. I hope you guys are okay. So this is basically
Where are the black holes?
we're getting to that. You came in the middle of the lesson. You were late, by the way. Got here earlier than you. So kinetic energy minus potential energy over time, basically. It's like it's how much kinetic energy is kind of left. Like, or it's like you can kind of understand based on equation. Like this is intuitive. An integral, basically, if you don't know, it's accumulation. If you haven't done calculus, this means over time, basically, for dt, because that's the change. Okay. So this balances kinetic versus potential. If you take in physics, yes.
So is action the amount of energy an object has, like, during its action?
What do you mean during its action?
Like, kinetic energy minus potential energy equals
Over time.
action? Oh.
Or like, I guess not over time, like in terms of over t, but in terms of like accumulating it over time. It's the accumulation of the entire path, like it's like how much of something there is, if that makes sense. It's kind of like it's kind of a unit. I don't know, it's kind of a weird unit. It's like not really intuitive, but this is like a way to think about it is that it's a whole thing. So the reason I'm saying this is that you can picture action as like, or well, maybe it's a bad thing. If I want to go from one point to another point, what line? Not like distance wise, but if this was one place and this is another place, and I want to drive, like what would minimize the amount of action I would do? Driving in a straight line. Correct. Now, what if, for chance, it was this point to another point. Gravity is now enabled, and you want to get down there.
So action is less.
What?
Action, there's less action in that? Because
This is just a different example. So it'd be still a straight line. So yeah, but then say if there's nothing there.
What?
I know, right? What shape gets you if you drop the ball, what shape minimizes the time it would take for that ball to get here? Yes, wait, do you know the name of that shape? It's called a cycloid. And it looks like this. But it's like instead of just going if you went like straight like that, it would take more time. If you did this, it maximizes or minimizes the time it takes.
Isn't this what airplanes do? Because they like go around the world instead of straight.
Yes. Good connection. That's kind of what we talked about that last week, but you weren't there for that. So no, sorry, that sounded rude. I was just saying. So okay, I'm just gonna expand this because so action value depends on the trajectory taken by the ball through x of t and v of t, which we don't have to go into. Actually, I guess we should go into the physics, but that's fine. So in classical mechanics, a system moving between 2 points takes one particular path, and other similar paths are not taken. But this is not the same for something like, say, quantum mechanics, where if you don't know, quantum mechanics is like the study of things on a molecular or an atomic scale, where it's less of a deterministic reality and more of a probability-based reality. So you might have heard something called the wave function, which is like, I think it's like represented by this or something. Or no, not. It shouldn't be an H. Sorry. It's represented like a psi, but it's basically showing like I don't know how I'm gonna draw this in 2 dimensions, but it's like this and then that and then you have like but like thing is this is kind of multivariable calculus, I guess, if you want to try and figure it out. Sorry, reference. Yeah, because there's a z-plane, and you're trying to find because it's not just this like line. Oh, what's this flat line? You know, it's a surface basically. So, but that's like when you think of that as this is not like this is one thing. This is what you're representing in quantum mechanics. It's not like a single point. Like you think about if you throw a football, you know, it's a football. It's not every football that can be thrown from. It's not a field of footballs all being thrown at the same time. But if you're doing this, then you have to take account like each one of these points is equally likely. It's just that there are more like they're equally likely, but they're accumulated some more so in some places. So that's how an electron works. Where if you have this is kind of a side tangent, but if you have like this is a terrible model of an atom. If anybody shows you this is a model of the atom, like embarrassment. This is what you learn. This is what you learn in middle school, but it's fine. But you have got a proton. I don't even know if I should even draw this. Like the plus. But you have a proton and you have an electron orbiting around it. But this is not actually accurate. It's just a way to represent it like mathematically, or not really. I guess it's terrible mathematically. It's actually kind of the opposite way mathematically. It's a way to represent it like logically with our brains without getting into probability mechanics. So in actuality, it looks more like this is what a single electron's. So this is the orbit we are told it takes. It just goes like a planet around a thing. What actually it does is it goes kind of like this is one electron, by the way. It goes kind of like, and then that is one singular electron. It's actually learning Chem C, which is how I know all this. Shout out Chem C. And that's for one singular electron, and that's for the lowest possible energy scale. Look at the higher energy scales. Like there's something called orbitals and valence shells. I'm not going to go into. I can do into this if you want, but basically the more excited an electron gets based on its like atomic number. So like uranium is obviously has more electrons than hydrogen. So uranium would have electrons that go more crazy because they have more electrons and they have to be higher energy for protons to attract and like keep them, because like this thing is like and then it has like a bunch of protons around it, versus this thing is like and it has like one electron, and that means that this thing has to be like strong enough to attract it. That also means the electrons have to be strong enough to resist it, and so that means they go higher speeds, or I don't know what speeds, but they have more momentum and more spin. More spin. I don't know. I'm not gonna get semantics, but yes, they have more energy, is what I'm trying to say. And so the actual thing, Nick, do you remember what it looks like? For the second stage, it looks like this, but then this is a probability, so it actually looks like
It's like
yeah,
And
basically.
it's also 3D.
What is that?
That's the second stage of electronic excitement.
The second stage of
Electronic excitement. This is the first stage. It looks like it's like a circle.
yeah, but it's like crazy.
Yeah, and then this one is more like infinity.
It's like a figure.
It's orbiting the proton. So the proton is
Why does it have stages for that?
I can do a different lecture about that.
Okay.
But that's a different stage because of what I was talking about here, where
When you get
more excitement.
electrons.
Yeah.
So the circle is just representing like all the probabilities are inside this range,
Yes.
and when you do the wave thing,
This thing?
no, that one,
This thing?
yes, that is it's like a line of where most of the it's like
Yes,
the
but this
average
would be
of
for
all-
a single electron.
Yes.
Or a single maybe not electron, a single particle. Any
it's like
one
the
particle.
average of a graph.
Yes, exactly. Well, you don't really think about it in average. You can do that to determine it. Like, so that's how we think of like particle-based physics, where it's, or let's think about, particle-based physics. This is wave-based quantum mechanics, where it's like You determine it. You kind of determine it as a matrix, which is also scary. That's actually scary. Matrix is a don't ask those questions. That terrifies me. Okay, I don't even know how I'm gonna fit this anywhere. Let's see. Let's do a matrix. Okay, so I have a system of equations. X plus y equals 2. Give me a second system of equations with these two variables.
Can Nick do it?
I'm gonna give you a what? Wait, what's the
What's a matrix? 2x plus or minus?
5.
Minus or plus?
Minus.
Okay, minus 5y equals any takers?
Well,
Okay, thank you. So, well, unfortunately, I'm gonna have to get rid of an electron.
No.
Sorry, buddy.
he asked, we're inserting numbers and then you can do something.
So you can represent this as.
Yes.
And now we're making him hella.
Well, actually, I should do this first. But
Are we explaining what a matrix is?
yes,
How does this relate to black holes?
it was a side question, and it's relevant. It is actually relevant.
Wait, wait to get back to the black hole.
Hold on.
You need to wait your turn.
I will lecture what I want to lecture. Okay, so you would have 1x, 1y, and you have 2 x's, negative 5 y's.
What is
The
that's
two
not
is
related to?
This is a side tangent. I'll get back to that.
That's not related to that.
You want me to? Oh, this side explain? Okay, so that's actually what I was supposed to be talking about.
Should we finish matrices at first? And then
Yes, that's what I want to do. I'll explain matrices and then matrices and then go. So then, how would you? This is how to represent it. You would go x and y, and then this equals. Well, there's a. I don't want to erase this, but it equals. This is horrible notation, by the way. Never put it below. There's like this is a thing where, actually, I'll get into this later, but the order of things does matter for this. So then that would equal 2 over 12. Or sorry, whoa. Shame on me. I wrote a over sign. Shame. Thank you. Equals that. So a matrix is a way of representing a system of information. Because what if you wanted to do 5 of these? If you want to do 5 variables. If you want to do X, that's a good question.
it'd be a long column in the parentheses.
It would be, but you'd have 5 different system equations. Or if you could technically have 1, but it'd be boring. If you want to have like a fun matrix, you want 5 system equations. You want 5 variables. Now, how would you graph that?
I don't know.
Exactly. The matrix is a way to graph the system equations without like going insane and doing like 6.
What does it look like? Just like
Okay, a 2D matrix gives you a plane. A one-dimensional matrix gives you a line, I think. Cordero, is that right? Does a two-dimensional matrix give you a plane or a line?
Two-dimensional matrix would send like a vector to a different place in the plane.
We're like solving it.
Oh, like a system of equations?
Yeah.
Well, if you solve a system of equations in 2 dimensions like that, you would get a point x by, no? Is that what you're asking?
Yeah, sorry. No, yeah. If you're solving it, then you get that. But I'm saying if you like, I don't know. I watched the lecture. It was weird. They had a cool thing. I can link it to you guys if you want. But basically, it's like, I think a single point would be one stage or one side vector, whatever. The point is, you represent them based like that, and then you go cube, and then you go I cry because how do you represent 4 dimensions?
Yeah.
Or this is a square. It should be like a cube, but I don't want to write a cube. So.
so then you cry. And matrices are to help you cry.
Matrices are to help you not cry.
Oh,
But-
what does it look like? It looks like a bunch of numbers and columns.
Yes, it's the same thing as this. You just expand the number. It's like 5 rows.
Draw a picture of it, but you can draw a number picture.
Yes, that's the point of it. Is to be able to draw a number picture without drawing an actual picture.
Because we don't know what 4 dimensions looks like.
We don't want to.
Yeah.
That's
because
what they do in Interstellar.
because you would cry.
Yeah.
Correct.
And that's why he cries.
Yes, that's exactly why he cries. Yes, because he has to. He's like, this isn't right. This doesn't make sense.
That's it. That's the opening reason.
Okay, I am probably gonna clear. How do I?
Destroy everything.
I'm destroying.
Oh man. No. Can we get back to the Wait, pick the plane.
Horrible. Horrible.
So explain why that related.
Well, Loki the Matrices isn't relevant to today's discussion, but it's relevant later. So,
I'm thinking
in the head. Okay, so going back to this. If it's a point to another point, then something funny happens. Yes, question.
What topic are we on now?
We're still on action. Sorry, we're not on matrices. We're on action.
How does action by the black hole?
That was what I was getting to. Two, what I began at the beginning of the lecture. But it's like, remember last week we were talking about the path of least action for a light to go from one point to another, and how space-time warps to make it so that light goes in a straight line. Yeah. No. I'm just messing, bro. Right, you can leave. That. Sure. Have fun with that one. Yeah. You like that?
Is it like a basketball?
In real life? That's crazy. Okay. So from this point to this point, something weird happens. You know how we talk about probabilities and stuff like that? That was actually relevant. Is that light doesn't just take one path. Because that'd be boring. Light takes the path that would be the least amount of action. But how does it know what the path of least amount of action is? Well, question?
Is the least amount of action the least amount of time?
It's the least amount of energy over time.
Let me think about that one.
Okay.
Because I forget. But I don't.
So like
If it's light, then yes.
Points, if this is the one that makes it
If it's light, then it's the least.
that have the less action.
If it's light, it's the least amount of time. If it's anything else, I think the energy is variable depending on what that is. So I think it's actually not necessarily that. Does that make sense?
But in the case of
Yeah,
light,
but if you have between those 2 points, if it's like this is.
Well, sorry, I'm about to explain some stuff.
Okay, great.
Okay, so why would it take one point, and why would it take one path, and how would it even figure out that path in the first place? Well, what if I do this path?
Oh my.
that's light path. Bro, that's not efficient.
That's what I'm saying, bro. That is not efficient. What if it actually came out? What if it warped imaginary dimension? Bang! It goes. Well, the screen can't see, but I'm walking out the door. Well, fun fact: this happens for everything. Yeah.
That's how light looks?
Yes. That's how light looks. But then also think about if light is a wave. Well, it's a particle on a wave. But for our purposes, it's a wave because we like ourselves. But that means as it's going, it's not really like a line. It's like a radiating. Bang. The light. Like that.
What are the lines?
This is like showing a wave.
Okay.
What? That's fine. No, I just don't know what science you're in. Which one?
He's a freshman.
Oh. So for that, this is a bit advanced. I'm sorry. So, but what do you guys know about wavelengths? What do you know about if I'm talking, somebody else starts talking? They crash into each other. Yes. And what does that mean? What would that do?
They're affected by each other.
Yes. And if you have one wave going like bang, and one wave going like this, like I'll do this.
Yes.
And then they go like that, and they go like that. What happens here? What?
They bounce it.
They destroy each other.
Well, what happens to I'll ask you this: what happens to a sine wave when it encounters? Whoa, is that yeah? When it encounters a cosine wave? That's not right. Whatever. Basically, but whatever. It's a cosine wave. They cancel each other out. Because if you do the value, well, I'll just do this, but like at sine of 0 equals 0, because like yeah, and then cosine of 0 equals, well, it starts up here, so it equals
Yeah, exactly.
pi over 2.
I thought it was like sine and then negative sign, they cancel.
Well, that too, but negative sign is just same thing, I think.
Also, that's one, not five.
Oh yeah, wait, sorry. I'm doing it, yeah, I was doing the wrong thing. I was doing it in radians and not, or no, that's also radians, whatever.
So what, you're doing arcsine and arcosine?
Whatever, you don't have to worry about that. Yeah, sorry, no, yeah, I reversed it, but
Oh, okay, I got it.
I just messed up. So, what that tells us is that if they're opposite, they cancel. If they're the same, they amplify.
So are they amplifying there?
I don't know.
Because they're going the same
I
direction.
forget. I know. So I'm gonna wrap this up. What happens for here is that all of the wavelengths, except for the path of least action, cancel out because they all are slight changes, or maybe not so slight in this case, changes to the how light travels. So actually, every probability happens. It's just that some probabilities cancel each other out, and they all amplify to get like a collaborative one true probability. It's not necessarily a straight line. Could be like this or something, but it gets something. Guess question.
Does light just test all the possibilities until it gets the best one?
That's our best theory of how light works. Don't ask me. I'm not a researcher, but you know.
Where does canceled out light go?
What do you mean?
Like when light is canceled out.
Okay, where does canceled out sound go?
I mean, it doesn't.
It gets canceled out. It's gone.
So the energy is just like
Yeah.